Introduction. The procedure for this lab is to use an online circuit construction kit to construct several different types of circuits, according to the instructions in the lab procedure. The main physics principles applied were circuits, series, parallel, including use of ammeters, capacitors, voltmeters, resistors, just lots of different types of circuitry, the energy conservation loop rule, and the current conservation rule, which includes charge conservation, the definition of steady state, which is the node rule. The first situation from this lab. So we have the original, where we have these two batteries, these two ammeters, and then we reverse the connections. So as you can see from this, the charge doesn't change on the ammeters even when you reverse the connections. That's the main point of this. My resistor values somehow, I think, may have gotten changed and adjusted the reading on the ammeters, but the main takeaway is that flipping the connection does not change the charge. Then we have the situation where we replaced one of the ammeters with a voltmeter. Before, the ammeter read 0.05 amps current through the circuit. I know that later in the lab, when I have everything situated right, it actually reads 0.02 amps, but in this case it's 0.05. The new readings on both these meters, the ammeter, there's no current through the open circuit, and the voltmeter reads -3 volts, which means that there's a difference of voltage of -3 between these two wire ends. So this voltmeter is reading this change of voltage, and the ammeter is reading the current that goes through it. Then we do voltmeter readings around the circuit after I've replaced that gap from the picture before with a wire. You can't see the readings in all of these, but I've highlighted above the readings that are not 0. So we have a reading across the batteries of 3 volts, and then readings across the resistors of -9.59 and -2.041, which gives us a total of 0 volts around, which agrees with our energy conservation loop rule, which is how that rule applies. So then I've graphed the potential versus position according to this loop rule that I explained before. So here you can see the peak, and then when it goes, the differences across resistors. When I attach the voltmeter, I alter the circuit. So why doesn't this ammeter reading change? It's because it's after the ammeter in the circuit. Then I create this parallel circuit, and you can't see the readings on the ammeters here, but the ammeters have the same reading. Then I do some calculations to calculate the resistance of the following elements. The resistance of the 47 ohm resistor is 47.95 ohms, as would be expected. The resistance of the 100 ohm resistor is 102.51 ohms, which would be expected. And the resistance of the wire is 0, and the resistance of the ammeter is 0. And I calculated all of these by we know that V equals IR, so we know that R is the change in V over I. For RC circuit with the 10 ohm light bulb, the light starts bright and slowly fades, and it takes approximately 15 seconds to fade. When I first connected the battery, the current is moving through the wire and then slows down, and the charge density increases on each side. When I disconnect the battery, the reverse happens. The current moves slowly and the charge density on each side lowers, and it also takes approximately 15 seconds. Maybe a little less, but I think that could just be an issue with the software. When we disconnect the battery, the light doesn't light up as bright or for as long. With the 20 ohm bulb, I have a very similar experiment, except it takes approximately 27 seconds, approximately 30, which would be approximately double the time for the light to fade and for the charge density to increase and then decrease. For the time-dependent circuit, this is the process for calculating this transient response time, this time constant. I know that T is R times C. I know that the charge on the plates is Q equals CV. And I also know from some reading and research that the time to charge is approximately 5 times the time constant. And then I also know that this voltage versus time graph has an exponential relationship. The graph feature on my CCK wasn't working, so I can't do a comparison, but I would hope that they would be very similar. Conclusion. What is the sum of the individual potential differences for a round trip around the circuit? What is the sum of the individual potential differences for a round trip around the circuit? My guess was they should be 0 because it's a closed circuit, and my result is they actually are 0. What if we were doing this lab in real life and used an actual ammeter? There would be more noise, it would be less accurate, and the current wouldn't be perfectly carried through. The ammeter also wouldn't have a perfectly zero resistance, so some of the voltage would be lost. What if we were doing this lab in real life and used a real battery to charge a real capacitor without a resistor in the circuit? It would take more time, it would lead to a smaller change in charge density and a dimmer light. Again, it wouldn't be a perfect circuit, and the ammeter and the wires wouldn't actually have zero resistance.